Okay, let's talk about theoretical probability distributions. These are distributions developed by statisticians over many, many years. A lot of research and thinking has gone into the development of these theoretical probability distributions. They can be used. They're very useful tools for specific analytical conditions. They are applicable to many real-world analytical problems that we might run into in science, business, medicine, you name the field, there are applications. They serve as an analysis shortcut. Instead of building our own probability distributions for analysis, we can use these existing probability distributions, assuming that our problem meets the assumptions necessary for using the theoretical distribution. I don't want to say the two most, or two of the most commonly used theoretical discrete probability distributions are the binomial distribution and the Poisson distribution. And I know that looks like poison with an extra S, but I believe it's a French word, and the pronunciation that I've always heard is Poisson, P-W-Asson, Poisson. So I'm not going to deduct any points if anybody pronounces that incorrectly. If you call it poison, that's fine with me. Both of these are useful in a lot of different applications, a lot of different business decision-making situations. But we're only really going to focus about the binomial probability distribution because of time constraints. The Poisson distribution is covered in your textbook. I will be making some videos on the Poisson distribution, but you won't be responsible for anything that I have on the Poisson distribution. So let's talk a little bit more specifically about the binomial probability distribution. Applies to experiments where there are only two possible outcomes. And these two possible outcomes are usually described in terms of success or failure. And success doesn't necessarily mean that it's a good thing, as I'll talk about as we move along here. But success or failure, whatever we're focusing on in our analysis, whatever we're wanting to find the probability of, that's going to be the success outcome. But more on that as we move along. Here are some examples of business situations where this could be useful. We want to calculate the probability of producing a defective item or an acceptable item. We have a manufacturing process. That's our experiment. This manufacturing process is producing two different outcomes, two possible outcomes. Either it produces a good item that's acceptable and can go out into the market and be sold, or it produces a defective item that's not something that the company can sell. Another example, probability of having an accident or not having an accident. This could apply to vehicular travel. This could apply to workplace accident scenarios, apply to a lot of different environments. Probability of winning or losing. You might be able to apply this to sporting events. Probability of making a sale or not making a sale could also be, we could also use this binomial probability distribution to find these probabilities as well. To use the binomial probability distribution, again, there are only two possible outcomes. There also needs to be a specific number of trials involved in the process. These binomial probabilities are empirically based. We need to know the probability of success and the probability of failure prior to using the binomial distribution and the binomial formula to find probabilities. So let's go ahead and talk about the formula that's in the textbook. There's nothing wrong with this formula, but as I go along here, I'll talk about what I think is a deficiency with this particular formula. We have probability of x equals some combination, that represents some combination, multiplied by the probability of a success on each trial, and that's to the power of the number of successes. That's multiplied by 1 minus a probability of success to the power of the number of trials minus the number of successes. I know that's a mouthful. I know that's I've lost you completely already, but it'll make more sense when we work through a problem. And here's our problem. This is from the textbook also. Recently, www.creditcards.com reported that 28% of purchases at coffee shops were made with a debit card. For 10 randomly selected purchases at the Starbucks on the corner of 12th Street and Main, what is the probability that no purchases were made with a credit card? Okay, what's the probability out of 10 purchases that no one used a debit card? That's what we're finding with for this problem. That's what we want to know for this problem. And we can use this formula. Again, this is the formula from the textbook. Let's go over again what we've got here. We've got a combination which is going to require a separate calculation using the combination formula from chapter 5. That's what I don't like about this formula. There's another formula that I want to show you where you do it all in one formula. You don't have to do another calculation so you have a value to plug into this formula. But let's go ahead and work through this one first. In this formula, n, which we have here, is the number of trials. That's going to be 10. X is the number of successes. And this is, when I said earlier, success doesn't always mean success. We're focusing on no purchases made with a debit card or a credit. I got credit card here, debit card, credit card. What's the difference? Anyhow, the number of successes here is 0, meaning that a debit card, credit card was not used. And that X, number of successes, is plugged in here and here. Pi is the probability of success, which is given to us in the form of a percentage. We'll need to convert that percentage to a decimal, and it shows up here as 0.28 to the power of x. In this case, x is 0. So that's all of our. Those are all of our numbers plugged in, and we still have to do this calculation. And when we do this calculation, it ends up being 1. So. But on the next slide, I'll show you the calculation that was necessary to find that value. Let's see, what else do I need to say about this? The symbol pi is used, but it's not the 3.1416 pi that we use in geometry. It's probability of success. Don't get confused and start plugging in 3.1416 every time you see this symbol. Completely different arena here. It's not going to work. Pi is our probability of success on each trial, which will be given to you, or which you will know from past research. In this case, it's 28% converted to a decimal. That is plugged in here and here. Okay, once we get it to this point, assuming that we've done this combination calculation, we have all of our numbers. And let's go ahead and subtract 1 minus 0.28. That gives us 0.72, which, by the way, is a probability of a failure for this particular problem. We have 10 minus 0 is 10, working on the exponent portion of this term. So now we take 0.72 to the power of 10. We end up with 0.0374 multiplied by 1, multiplied by 1, we find that the probability that no purchases were made with a credit or debit card out of these 10 trials is only about 4%, 0.0374 probability that a credit card was not used. Okay, let's take a look at the calculations that were required to get the one term. We had to do this calculation to get this and plug it in. What, going the wrong way here. We had to do that calculation, that 5 or 6 step calculation to get this term here. Let's look at another example. The same data that we used in the previous example, but we want to know the probability that exactly one purchase out of the 10 was made with a credit card. Plug in our values. The probability of success is still 0.28, so we plug it in everywhere we see the pi symbol. The number of successes is 1, so we plug it in for x. The number of trials is the same at 10, so we've got all our numbers in. The combination formula yields a value of 10. 0.28 to the power of 1 is 0.28. 1 minus 0.28 is 0.72. 10 minus 1 is 9, so we have 0.722 to the power of 9, or the ninth power, which is 0.0520. 10 times 0.28 times 0.0520, we end up with a probability of about 14.5% that out of 10 purchases, one of those purchases will be made with a credit card. And you may be wondering, well, who cares if they use a credit card or not? Well, the businesses might care because there can be additional charges, additional overhead for businesses for processing credit cards or debit cards. So this is kind of trivial in a way, but it does have some business application. And here is the calculation required to come up with the combination value on the previous slide. There's another way, and that's what I want to show you now. There's another formula. It does not require a separate calculation for the combination component. And this is not in your textbook, but this is the one I would use if I'm using a formula for calculating a probability, a binomial probability. This is it. Let me talk about the different components. We're finding the probability of X number of successes. That's what we're finding. N is the number of trials. X sub 1 is the number of successes. X sub 2, the number of failures. Then we have X sub 1 here and here also. P is the probability of success on each trial, which it's the same as pi in the other formula. And P is there. And Q is the probability of failure, which is 1 minus P. So, and already to me it's much more straightforward. I mean, you do have to use the factorial function, but that's easy with your calculator. Factorials are no problem. If you have the calculator, that'll do it for you. So let's go ahead and do one of the previous problems using this formula. From the previous credit card problem, what is the probability that no purchases were made with a credit card? Start with our formula. We have 10 trials, that's N, so plug in 10. For N. We have 0 number of successes is what we're looking for. and 10 is the number of failures that we're looking for. The probability of success on each trial is 0.28. The probability of failure on each trial is 0.72. We also plug in the number of successes as an exponent here, and the probability of the number of failures here. Again, number of successes here, number of failures here. 10 factorial, 3,628,000. 0 factorial is 1. 10 factorial again, 3,628,000. 0.28 to the power of 0 is 1. 0.72 to the 10th power is 0.0374. We end up with the same probability that we ended up with using what I consider to be a more labor-intensive formula. Yeah, and it's up to you. You can use whichever formula you want for the homework and for the exam. But if it's me, I'm going to use this formula because it saves you a major step, because you don't have to have that separate calculation for the combinations. All right. I'm going to go ahead and stop this video here. We've talked about the different formulas we can use to find binomial probabilities. We've talked about binomial probabilities as a theoretical distribution. In the next video, I'm going to show you how you can use these formulas to build a probability distribution for all possible events that you may be interested in for your particular analysis.